Surface areas. We refer to surface areas as the actual thermal envelope of the building in all three dimensions. Um, so as in the walls, the roof, and what's happening on the ground. Um, the surface areas have an effect on the performance in terms of the heat transmission and, of course, the thermal gains that the building can make. We refer to something called the form factor, which is basically looking at the heat loss area, as in the envelope of the building, and dividing it by the usable space, which we call the treated floor area. And if the heat loss form factor is less than 3, it's usually a good benchmark guide that the building will perform as a passive house. The more complex the shape of the building, the more surface areas there are for the same piece of accommodation, the more heat loss potentially, and therefore the harder it would be to get it to passive. This might mean improving E values or improving thermal gain to make up for that. It doesn't mean to say that good architecture isn't really important. It just means that we need to consider weighing up the complexity of adding perhaps little dormer windows, which might look good from the street, but are they really necessary? Or maybe taking a different approach to the design that simplifies the surface areas. We take into account the roof pitches, location, size of the windows, the doors, and the roof lights. We look at the ground, the conditions of the ground, whether it's sitting above the ground on a suspended floor, whether it's actually got a basement, or whether it's on the ground itself. And we consider the perimeter, which also is reflective of the form factor. The more perimeter, the more areas around that might lose heat. And all of this gets precisely modeled in PHPP and informs the outcome of the building. And when we choose our components, and when I say components, I mean things like perhaps some products in the building construction, and also some services like MVHR, or perhaps glazing, or doors, things like that. Components that you purchase as an item that might go into the construction building. And there are two ways to approach this. There is a database of Passive components, and they're on the Passive Institute website. And those companies have chosen to have their components certified by the Institute to verify that they would actually perform. For example, if you were to buy some French doors or sliding doors, you'd want to ensure that they had the correct thermal breaks in the frame, and that perhaps they had a good class 4 wind factor, which would stop any air leakage in the actual product. And these companies will have gone through the process to get their products tested to say that they're a certified component, they are suitable for use in a passive house. However, that's not the only route. We can also use non-certified components, and the only difference is that we're working with perhaps independent manufacturers who haven't gone down a certified route, that they would be happy to validate and provide evidence to comply with pH criteria. So we would ask them to give the technical data and the documentation that would support a satisfactory design or accreditation, and then we can share that with the Institute to check that these products are okay to use. So it's not necessary to feel that one's pressurized to use passive components, and sometimes people feel very anxious because they might cost more. And in fact, they don't always cost more, and they're sometimes better. But don't ever think that you can't try the non-certified route as well. It just need to be backed up with the correct documents to show that they've worked through and the product actually does what it says. Okay. Um, Windows and shading. As we all know, we need to allow the warmth from the winter sun, but perhaps limit the solar thermal gain during the summer months. This summer is a classic example of that, where perhaps it's been a little bit too warm inside some homes and buildings. The summer sun obviously comes at a higher altitude through the sky, and the winter sun lies at a lower one. We've obviously got the impact of the surroundings that we talked about earlier. Are they deciduous trees or are they evergreen? Um, Buildings obviously permanently there. And so all of those factors we would consider in seasonal shading, and then come up with a proposal that would address that concern over having overheating in the summer, and perhaps by fixed or operational shading. One obviously relies on either um, it, a manual operation or an electronic operation, and the other is a fixed item that is part of the architecture of the building. It just stays there. And externally fixed we call them brise-soleil. They're like the louvered canopies, or we can have overhangs, perhaps some other parts of the building, and or natural solid forms, like fir trees and things that are always there. Internal, we can have frosted or opaque glass that reduces the amount of sun that can come into the building. Operational would be more of a rollout canopy or folding shutters, or perhaps scroll down shutters, or internal blinds that you pull down, or internal shutters. All of these rely, as I said, on the occupier, and perhaps if they're forgotten over the course of a hot summer's day, if they're not applied, they might come back after work or their day out and find that the building's a bit warmer than they'd hate. And the other thing that's quite interesting is that if we can stop the heat coming into the building in times that we're concerned about overheating, it's better to address the problem from the outside than the inside. And the reason for that is that once the heat has come into the building, even though we're putting in a blind or shutter or frosted glass on the inside, it's already in the building. So it's already causing heat gain. It's just we're controlling the spread of it. And I'm sure we've touched on this in other modules, but I thought I might just mention that glass and frame properties have an impact in the PHPP. It's quite a specific set of data. This diagram's really helpful to indicate the amount of energy, solar thermal energy that comes through the glass. There's some reflection, there's some direct transmission, there's radiated heat and internally radiated heat. These all work together to give us our solar factor, which we call the G value of the glass. The G value of the glass can be orientation specific. So, for example, you might require different performance of your glass on the north face and the south face of the building. And we would obviously help with the specifying of those triple glazed units. I know that's double, which should be triple. So we'd also address a nighttime ventilation strategy. So when you're sleeping, perhaps you want to have a little bit more of a cool down. How would we do that when we're thinking about security, privacy, safety as well? We'd have a daytime ventilation strategy, perhaps first thing in the morning or in the evening, with just to let some air through the house. And as I say, we talk about security, privacy. So in the windows and door values that are chosen, we have very specific items that we cover: the U value of the glazing, the G value of the glass, and the U value of the frame, as well as the psi values. Now, psi values are basically the thermal bridges where the frame meets the construction of the building. So the details that we put together to address the continuity of the thermal envelope to try and keep the psi values down as much as possible. Internal heat gains. These basically come from the use of the building, perhaps domestic hot water and heat pipe runs, building services within the building, humans, animals, general occupancy, and quite importantly, plug loads and appliances, whether these are in an office, computers and TVs and fridges and things like that for a home, washing machines, dishwashers, laptops, all these sorts of things. It's really important that we consider the performance of the appliances, going for as high an A rating as we can to get efficiency. And also to rationalize any design at an early stage so we don't have very long runs of hot water going through the building from the source to a particular area where the hot water is needed, for example. To avoid the overheating, in principle, we talk about stress testing. So we address whether or not what would happen to the building if no one shut the blinds? What would happen to the building if suddenly it was double the occupancy? What would happen to the building if any other aspect failed? The internal heat gains went up, so perhaps the use of the building changed and it was a different amount of appliances or systems within the building. We have a criteria that we put together to test that, and we always try and make it work so that it's got comfort and performance based on our strategy for the building. We don't want high internal heat gains to tip it the other way. We don't want poor UVs to tip it the other way, and we don't want the incorrect glazing, shading, ventilation strategy to tip it the other way. We want to future-proof the building for future climate change and future uses so that it actually performs and is comfortable to live. So, thank you very much. That's the end of PHPP. Okay.
Yeah, brilliant. Thank you, Claire. Some good questions for us to pick up on and just understand the practicalities of some of the things that we talked about there. So I know that you mentioned PHPP as being a design tool specifically for designers. How might somebody involved in the construction industry, how might he have a relationship to PHPP and the design there?
Oh, totally, yes. So if you can get PHPP training in both design aspects and tradesperson's aspects, the difference perhaps is that the tradesperson might look at specific aspects of the PHPP relative to their skill set and the approach to the building, and you can try a few variations on the design based on that, and share that with the overall approach to the building, or perhaps have the overall approach to the building, and then choose to evaluate what would be the best approach for what they're doing.
Okay, yeah. So you mentioned skill set there. So there's an understanding of, I'm interpreting it that, all right, we're looking for this outcome. We're going to use this strategy based on the PHPP. Who in the team is capable of managing this? Is that what you mean, or have I misinterpreted that?
I think it's just about communication. Everybody has an input, as long as we all know what the current decisions are, and if there's options and variations, share them, test them in the PHPP, and make sure that the outcome is what we're working towards.
So you could almost say the PHPP is a communication tool.
Yes,
Almost, yeah.
absolutely. Yes.
Good
We
stuff.
have variation aspects of the PHPP where we can say, well, if we did this approach, perhaps with MVHR or with the heating system, for example, how would it perform? If we did it a different way, something that needs to be tested or tried, we can see whether that's better or not.
Excellent. So we are actually inside Claire's retrofitted, we call it the barge, NFIT standard retrofit. And so let's bring it to life a little bit. How did you use the PHPP and make design decisions and practical decisions with this retrofit based on the information that you were getting from PHPP?
Oh, that's a big question. I think one of the biggest yet simplest ones to explain would be the thermal performance of the building, and so the actual U values. We have I can't remember how many, but it must be coming on for 8 different wall types in the building because it's wrapped around by different party walls and different building ages. So we have lots of different constructions going on, and it was trying to find a way of insulating tool that ensured that all the walls were as equal to each other as they could be, using PHPP to evaluate that, and then also having to think about other aspects and that we can go on to another time in terms of the science of the performance. Yeah.
Yeah, so if you had 8 different wall types that all had an end goal of being consistent to achieve the outcome that you wanted, which was an NFIT standard home, and you would have had to implement different levels of thickness, different types of insulation, and also consider how those different types of insulation connect and um, work in harmony with those different fabrics.
Yeah, that's right. Yeah. So it's really helpful like that because it takes the overall building approach. So it looks at all the parameters, and therefore you're not just constantly looking at one space in isolation.
Yeah, so the term whole house retrofit is something that's used quite a lot. So this PHPP format enables you to really look at the whole house in a lot of detail, and the prediction capacity of the PHPP is very accurate.
It is, and so passive houses have been around for quite some time now, although not so prominent in the UK. And there is an awful lot of data being correlated on the performance. So we all have these little monitors in each room of our house that tell us the relative humidity and the temperature. And they are almost like the backup proof that what the building says it's going to do, it actually does.
Yeah, so we talked about lambda values, and you did pick up and go into a bit of detail. I just thought we'd just open that up again and just get you to sort of slow it down and just tell us again what lambda value is. And we have talked about this before on the course, but I think repetition is the mother of skill. So let's hear it again.
Okay. Lambda. I love the sign. It's a good sign for a value. Lambda value for thermal conductivity of any single item in the build-up of the fabric. Okay? So it is the watts per meter Kelvin, the conductivity of the material itself. When we put the thermal conductivity into a building, so we say, right, that insulation has a lambda, let's say 0.03 watts per meter Kelvin. Take the thickness that you want to use, for example, 100 millimeters, that's 0.1 of a meter. Divide it by the lambda, and that gives you the resistance, thermal resistance, meter squared Kelvin per watt. of that particular product. The resistance is higher the better with the resistance, the more it can resist the transmission of heat through it. Thermal conductivity, the lower the better. 0.03, 0.02, good lambda values. You don't have to worry about all these sums in terms of if you'd like to, you can, but the point is that when we ask for a material, as architects or pacifiers and people, we're asking for the thermal conductivity of a specific product to be X. If it's substituted by another product, which is also, for example, EPS, if it's substituted for another EPS, the press is sold readily at the building.
So an EPS is basically
It's a rigid insulation board. That's good. And we tend to use XPS in places where there's more content, moisture content, or higher loads bearing, as in underfloors and things like that. But EPS you might, or PIR is the other one, I think.
yeah.
So if you go down the builder's merchant and you say, could I have some insulation, they won't necessarily understand what the lambda value, or have appreciated, that's be wrong to say they don't understand, but wouldn't appreciated the lambda value. So they might say, oh, we haven't got any of that in stock today, but we can give you this one instead. Is 50 mil of insulation. So say you want 50 mil, I've got 50 mil. It might only have a lambda of 0.04 as opposed to 0.036. I know that's only 0.04 of watts per meter Kelvin, but I promise you it would make a massive difference over the surface area that may have been specified in. So when we ask for the performance criteria, it's to do with the thermal conductivity. The PHPP then does all the rest for you. But I just wanted to show the context that the resistance material is based on the thickness divided by the lambda, and the U value is 1 over all the resistances, including the environment, the context-specific environment of where you're going to use the product. And that's why U values are slightly unreliable if someone stated a U value, because it might not be the context that you're choosing to use it in.
Okay, so